This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Okay, good morning everyone. So the plan today is to continue looking at Nyquist stability criterion. So this is a method for assessing the stability of a feedback control system or a feedback interconnection of two systems. So as we saw last time, we're trying to determine how many zeros this rational function has in the right half plane. The zeros of this rational function are the closed loop poles. Okay, lambda here is the open loop transfer function, the product of the plant and controller transfer function. So we know that the zeros of this are the closed loop poles. All right. So we also want to make sure that this has no zeros on the imaginary axis because we don't want any closed loop poles on the imaginary axis. So that's simply a matter of checking that for all frequencies, the open loop transfer function evaluated at s equals j omega is never equal to -1. All right? And to determine how many zeros this rational function has in the right half plane, we can apply Cauchy's principle of the argument. So as we saw last time, Cauchy's principle of the argument allows us to keep track of the phase of a function as it's evaluated around a closed contour, and we keep track of the net change in phase, and the net change in phase will be the difference between the number of zeros inside that contour and the number of poles inside that contour. All right? So we know how many poles this has in the right half plane. Okay, it's equal to the number of open loop unstable poles. All right, so we're going to apply Cauchy's principle of the argument to find out how many zeros this has in the right half plane. So we work with the so-called Nyquist D contour. That's this contour here. All right, which as we take the radius of this part to infinity will cover the whole of the right half plane. So the way we apply Cauchy's principle of the argument is we evaluate not this, but just the open loop transfer function at points along this contour where we make little indentations around the open loop poles on the imaginary axis so that we end up with finite points so that we can keep track of how phase is changing as we move along this contour in the clockwise direction. So we're mapping points along here to new points in the complex plane under the open loop transfer function. That gives us a new contour in the complex plane. And if we count how many times that new contour encircles the critical point -1 in the clockwise direction, then the number, and call that n, then the number of zeros of this function in the right half plane, in other words the number of closed loop poles, will be n plus p, where p is the number of open loop poles in the right half plane. So for closed loop stability, we want z to be 0. Okay, we want to make sure that we never touch the critical point because that would put closed loop poles on the imaginary axis. All right, and so for closed loop stability, we need the number of encirclements made by the polar plot of lambda when evaluated along this contour to be equal to minus p, the number of open loop poles in the right half plane. Okay. So we started looking at some examples. All right. The key thing is that most of the time we're evaluating the open loop transfer function just along the imaginary axis. So it's like we're looking at the frequency response of the open loop transfer function. All right. But the open loop transfer function may not be stable. Okay, so you really can't think of that as the gain for sinusoids in, giving sinusoids out, because that only happens for stable things. But we can still evaluate a rational function anywhere we like, as long as it's well defined. And so what we're doing is evaluating most of the time lambda along the imaginary axis. When lambda is strictly proper, evaluating around here as the radius goes to infinity will just put you at 0. And so you'll be at 0 all the way along here. All right? And we know for every pole that we go around in the way shown here, with a little epsilon indentation, there will be a net change of pi radians of phase, okay, for every pole that's inside here. Okay, and of course when we're determining P, we don't count those ones, right? We only count the ones inside the contour. All right? So we started looking at this example here, right? So it's a system where the open loop has 2 poles at s equals -1. Okay, so that tells us that P is equal to 0. As we're evaluating this function along the imaginary axis, okay, we're really just getting new points in the complex plane. Okay, those new points will look like this. Right, for each frequency, we get a new point in the complex plane that has real and imaginary part. Okay, as we increase the frequency, we get different points. Okay, so each point along here corresponds to a different frequency. All right. Now, for this function here, this is the Nyquist plot that you get. Right, so you can think of, it's good to think of where you start. So let's think of starting at low frequency. All right. What would you expect the phase of this to be at low frequency? Well, it's 2 stable poles, so you'd expect the phase to be close to 0. Okay. And we know that the phase of each stable pole as we increase frequency will go from 0 to -90. All right. So as we increase frequency going up this part of the Nyquist D contour, you would expect the phase to decrease from 0 towards pi, minus pi, right? And that tells you that it's going this way as we move up here. Okay, this is a strictly proper transfer function. So as we evaluate around this part of the Nyquist D contour and let the radius of that go to infinity, we get stuck at 0. So for the whole time we're going around here, we're stuck at 0. Of course, the phase of the function as we're going around here is changing, but what's the phase of 0? Or anything you like. All right? So we go around this contour, stuck at 0, then we come back up the negative imaginary axis. And as we're going back up the negative imaginary axis, we get this part of the Nyquist plot. It is just the mirror image in the real axis of the part that we got going up here. That's a property of real rational transfer functions. Right, the point -1 for this plot, this is -0.4, so the point -1 is somewhere over here. Okay, so if we count the number of clockwise encirclements that the Nyquist plot makes of the critical point -1, it's clearly equal to 0. It doesn't encircle this point at all, so that tells us that n is equal to 0. The number of closed loop poles, which are the number of zeros of 1 plus lambda, is equal to n plus p, that's 0 plus 0, it's equal to 0. Okay, so closing the loop around an open loop transfer function that looks like this will result in a stable closed loop. Okay. Let's look at this example here again. We have 1, 2, 3 open loop poles. All of them are stable. There's one at s equals -1, one at s equals -2, one at s equals -3. Okay. As we start here on the D contour and increase frequency, you would expect the phase of this to change from close to 0, right, at very low frequencies, to -3 pi on 2, right? Minus pi on 2 for each of these poles at high frequencies. Okay, all the time becoming more and more negative. Okay, so that's consistent with starting here and moving around like this. And if you zoom in here, you'll see that as it comes in, it's coming in at an angle of -3 pi on 2. All right, so I'd encourage you to think in terms of both the Bode plot and the Nyquist plot when trying to understand which direction you're moving around. Okay, think about what's happening at low frequency, think about what's happening at high frequency. Okay, so again, as we go around this part of the contour, we're stuck at 0, right? So every point along here under this function, as we take the raised to infinity, gets mapped to the point 0. Okay, and then we come out the other side. As we come out the other side, we just get the mirror image of what we got when going up here. Okay, so if we count the number of open loop poles in the right half plane, okay, you only count the ones in the right half plane, not the ones on the imaginary axis, okay, we get 0. How many encirclements does this make of the critical point? Well, there's the critical point, and so this doesn't encircle it, so n is equal to 0. So if we just wrapped a feedback connection around this open loop transfer function, we would get a stable closed loop. All right? Now let's think about what would happen if, instead of just wrapping the feedback loop around lambda, we scaled lambda. Okay? What will happen in terms of stability of the closed loop? Well, think about what happens to the Nyquist plot as we scale lambda by k. Remember that this is just a polar plot of lambda, right? Real and imaginary parts as we evaluate lambda along this contour, right? So if we're now going to evaluate k times lambda, each point here, right, which is just a little vector, has a real and imaginary part. There's the real part, there's the imaginary part. If we're just scaling by a positive constant, and that constant is bigger than 1, then all that will change is the magnitude, right? The phase will stay the same, okay? And if we scaled by a number less than 1, then we would get a point somewhere along here below the original point, okay? So the key is that the phase doesn't change, it just scales the magnitude. Okay, and that would happen for each point. So let's say we're working with a number k bigger than 1, so it's going to map this point to out here. Okay, let's say it's about 0.7 or something like that. This point here will get mapped out by the same factor. Okay, this point here will get mapped out by the same factor, and so it's like the contour is now looking like this for k equals say 0.7. If it was 10, then we would get points further out still, okay? So the plots, as we multiply by a constant, is just expanding and shrinking, all right? It's not getting rotated in any way. So we can see that if we were to scale this nominal open loop transfer function by a number bigger than 1 that takes this point to the other side of the critical point, it would be like saying the critical point is inside here, all right? And we would get 1, 2 encirclements in the clockwise direction, all right? And so if we're getting n equal to 2 and we've got p equal to 0, then we're going to get z equal to 2, and z is the number of closed loop poles in the right half plane. So if we scale this up by a sufficiently large constant, okay, we'll end up with 2 unstable closed loop poles. And that's consistent with what we would see by doing root locus analysis, right? So let me just draw that picture again, rather than dealing with one last time. So we've got a pole at s equals -1, a pole at s equals -2, a pole at s equals -3. Okay, so if we look at the root locus plot, we know that for small values of k, we're going to get closed loop poles that are close to the open loop ones, right? So we'll get 1 here, 1 here, 1 here. As we increase k, this one goes to an asymptote at an angle of -pi. The relative degree here is 3, so there'll be asymptotes at -pi, pi on 3, minus pi on 3. As we increase k, this one moves this way, this one moves this way. Eventually they meet. When they meet, they split apart in order to continue satisfying the phase condition that defines the root locus. And as they split apart, these ones go towards the asymptotes at plus pi on 3 and minus pi on 3. Right? So eventually the angle of this will be pi on 3 and minus pi on 3. Okay, and for sufficiently large k, we end up with 1, 2 closed-loop poles in the right half plane. Okay, so this is just another way of seeing that sort of thing. Yep.
When the value of k is having a complex conjugate, is the system acting as a underdamped system?
The value of k here is just a real number, right? If it were a complex number, right, then you would be changing the phase of each of these points, right? Each point here is a complex number. And if I multiply by a number with a non-zero imaginary part, I will be changing the phase, all right, as well as the magnitude. Okay, so the key here is that we're not changing the phase when we're considering this. Okay? You could think about what happens when I change the phase, right? We'll get to that later on today. Okay? But, you know, why think in this way? Well, because in design, you might be having to make decisions, right, about what the open loop transfer function needs to look like. Remember, it's the product of the plant and controller transfer function, and we're trying to design C. So we might choose C, we get a Nyquist plot, right, and then say, well, what happens if we increase the gain, maybe to reduce the steady state error? Okay, what's going to happen to stability? Well, we can use a Nyquist plot and the Nyquist stability criterion to help us understand what's going to happen when we make an adjustment to the controller that we've designed. All right, so it's a tool that's useful. Okay. All right, let's continue looking at some more examples. So let's take an open loop transfer function that has a pole at s equals -1, a pole at s equals 2, and a pole at s equals -3. All right. So in this case, we have an open loop pole in the right half plane. So we're going to get P equal to 1. Okay. Now, what does the Nyquist plot look like? Well, it corresponds to evaluating this function along the Nyquist D contour, right? Nyquist D contour is this thing here in the complex plane. Okay, so we're going to start here at omega equals 0. All right, at omega equals 0, what would you expect the phase of this to be? Well, we'll have the phase of a stable pole, another stable pole, they'll be at 0. We've got the phase of an unstable pole. What's the phase of an unstable pole? Where's that going to start at low frequency? It's going to start at minus pi. Right, and as we increase phase, it'll go to minus pi on 2. Right, so we're going to start with the phase of minus pi. Okay, so that's this point here. All right, and as we increase frequency, where are we going to end up? We're going to end up at a phase of pi on 2, minus pi on 2, plus minus pi on 2, plus minus pi on 2. Right, so it's going to be minus 3 pi on 2. Right, and if you zoom in to here, you can see it's coming in here at an angle of minus 3 pi on 2. Okay, so whoops. So when we start here and increase frequency, we're going to start here and move around like this. Okay, again, it's strictly proper, so around the D part of the D contour, we're going to be stuck at 0 for the whole time we're going around here, and then we come out the bottom and move up back towards 0, and we get the mirror image of what we had before when going up this part of the D contour. All right. The critical point is here, right? That's the point -1 plus J0. Okay. We clearly make 0 encirclements of that point. Okay. And so we will end up with 1 unstable closed loop pole. Right? Scaling this function, right, by a positive constant k, all right, will potentially shift this point, if k is large enough, to the other side of the critical point, all right, and we would get n equal to 1. But in that case, we would have two unstable closed-loop poles, because we have n equals 1 plus p equals 1, 2. Right? So increasing the gain here doesn't help achieve stability. Right? If we multiplied by a negative number, real number, okay, what's that going to do? It's going to change the phase of everything by the phase of -1. Right? What's the phase of -1? Pi. Right? So it's going to rotate everything by pi. Okay, so that will come over here, right? It will basically just flip. Everything rotates by pi, right? So it'll flip over here and go around like this. Okay? No matter how big that negative number is in magnitude, it still won't help us encircle the critical point. Because we have an open loop unstable pole, we need, right, an anti-clockwise encirclement of the critical point to achieve closed loop stability. All right? There is no gain we can choose here, positive or negative, that makes this encircle the critical point one time in the anti-clockwise direction. So we can never just close the loop around this and get a stable closed loop. Right? We would have to put some extra things that vary with frequency in order to get the required anti-clockwise encirclement of the critical point. All right? Let's look at this example here. Yeah, and I would encourage you, think about a root locus plot for this. Well, I don't know, let's just do it. We've got -1, -3, and 2, okay? So for small values of k, we get points like this. Okay, as we increase k, this one moves this way, this one will move this way, right? This one will move this way. They'll meet together, but in this case they meet together in the right half plane, split apart and go to zeros at infinity along asymptotes of pi and 3 and minus pi and 3 angle. Okay, so for small values of k, we've got 1, okay, and for large values of k, we end up with 2. Right, that's entirely consistent with what I just said on the basis of this being the Nyquist contour. Right, so there's lots of information in these plots. Right, they're not just things that we do for fun, they tell you a lot. Okay, all right, so try to think of these things in terms of all of the tools that we're seeing. There's not just one tool and you use this tool for this job and that tool for that job, right? All the tools are useful, almost all the time. All right, they give you slightly different perspectives on things, right? So don't try to match tools to problems. Okay, tools are tools, problems are problems. You might use 2 of the tools for a problem. Okay. Let's look at this example here. We've got one open loop pole at 0, okay, which is on the imaginary axis, and one at -1. So the Nyquist decontour has to be adjusted in this case to go around the pole at s equals 0. Right? So this is, epsilon minus epsilon. We're going to let epsilon go to 0, but we've put this little indentation around the open loop pole at s equals 0. Okay. So this is the Nyquist plot that you get by evaluating lambda along this contour. Okay, it's a strictly proper transfer function. As we're going around this part, we're going to be stuck at 0. Okay, think about the phase of this at low frequency. What's the phase of this going to be at low frequency? So when we're here, it's going to be minus pi on 2, right, because of the pole at s equals 0. Okay. So really, when we're evaluating lambda here, we're going to get something with very large magnitude. All right? Because, we've got 1 on epsilon here, and epsilon's very small. So the magnitude of this when we're here is going to be very large. It's not shown on this plot. Really, that point should be down here somewhere at an angle of, minus pi on 2, and then it comes up like this. Okay? And as we go up this part of the Nyquist contour, we're going to move to a situation where we're going to end up at a phase of minus pi, right? Because we'll have minus pi on 2 due to this guy and minus pi on 2 due to this guy, right? And that's what's happening. It's coming in at minus pi. All right, so that's how you can identify this as belonging to this part of the Nyquist decontour, right? Starting from low frequency and increasing, right? As we go around this part, we're stuck at 0. Then we come out the other end and we just get the mirror image. So really this is going up to an angle of plus pi on 2. All right? But we can't draw on this small plot where it really is. Okay? Okay. Now, as we go around here, we know we're going to get a net change in phase of minus pi radians. Okay? You get minus pi radians change of phase for each pole you have inside the indentation. We have 1. Here's your net change in phase of pi radians, minus pi radians. Okay? If you like, continue drawing this guy up like this. It's going up to an angle of there, and here's your net change in phase of minus pi radians as we go around this part. Okay? So the critical point is there, right? As we're going around here in the clockwise direction, we're going like this, right? How many encirclements of the critical point have we made? 0. Okay? So we've got P. What's P? Well, P is 0. Sure, the open loop has this unstable pole here, right? But we don't count that because it's not inside the contour. All right? So P is 0. Okay, we have N equal to 0. We don't encircle this, right? And so the closed loop will have 0 poles in the right half plane. It'll have none on the imaginary axis because at no point along here do we hit the critical point. If we scale this by a constant k, okay, what's going to happen? Well, in terms of the number of encirclements of the critical point, that won't change, right? Because this point is at 0 and we can scale 0 by however much we like. It'll stay at 0. Okay? These points will get extended along the rays, right? They'll get extended along the rays, but you'll still never encircle the critical point. So I can scale the gain up of this as much as I like. Again, think about the root locus plot. We've got a pole here, a pole here. For small values of k, we're close to those. As we increase k, that one moves that way, that one moves that way. They meet and split apart and go to zeros at infinity along asymptotes at angles of pi on 2 and minus pi on 2 because the relative degree is 2. So no matter how big I make k, I'm always in the left half plane. And you can also see that from the Nyquist plot. Okay? The main point here is that you don't count this, right, when determining P, because it's not inside. Okay? And the other point is that as we go around here, we get minus pi radians change of phase. All we're doing really here is keeping track of how the phase changes in order to determine the difference between the number of zeros of a rational function and number of poles of a rational function inside a particular region of the complex plane. Consider this example here. We have a pole at 0, a pole at 4, okay, all right, we have a 0 at s equals minus 1, right? So P is going to be equal to 1, right, because we have one open loop pole in the right half plane. We don't count that one there. The fact that there's a 0 is just not relevant, right? It might play a role in determining, the direction of increasing frequency when trying to figure out which way we're going around this plot. Okay, so think about what the phase of this will be at low frequencies, right? The phase of this pole at s equals 0 at low frequencies is going to be minus pi on 2. We've got an unstable pole. The phase of that's going to be at minus pi. So we're going to be at a phase for low frequencies of minus 3 pi on 2. All right? So that suggests for low frequencies we're going to be having a large magnitude, right, because we've got 1 on S on the bottom, we've got S on the bottom, and the phase is going to be minus 3 pi on 2. So it suggests we're going to be up here for low frequencies. And as we increase frequencies, come down, right, and approach that point there. You could figure out, what the phase should be at high frequencies, right? So it'll be minus pi on 2, minus pi on 2, that's minus pi, but you're going to get plus pi on 2 from the 0. And if you zoom in here, sure enough, we approach at an angle of minus pi on 2, which is where you would expect the phase of this to be at high frequencies. Right? So we're going in this direction here. It's a strictly proper transfer function, so as you go around the curved part of the Nyquist D contour, you're stuck at 0, then you come out the other side and go up the negative imaginary axis, and you get the mirror image. Right? So we're going like this. All right? As we go around the little indentation around the pole at s equals 0, we get net change in phase of minus pi radians. There it is. Moving minus pi radians is in the clockwise direction. Okay? Minus pi clockwise. Okay? So this is what you get. All right? What we're doing is this, right? When we're here, we're up here somewhere, right? As we increase, we're coming down like this, right? Ending up at 0 by the time we get here at a very large radius, going around here, stuck at 0, coming out the other side, around like this. And as we go around here, we get a net change in phase of minus pi radians. Okay? So you can see that we're now getting an encirclement of the critical point minus 1. Okay, it's in the clockwise direction. All right, we've got p equals 1, we've got n equals 1, so we're going to end up with 1 plus 1 unstable closed loop poles in this case. All right. Now, let's say we scale this again by a positive constant. Right, that's going to shift that point to the other side of the critical point. Right? And if we shift that to the other side of the critical point, it's like having the critical point inside here. Right? And in that case, you would get an encirclement of the critical point in the anti-clockwise direction. So if we make k large enough, right, we'll get n equal to minus 1, such that n plus p is equal to 0. So to get a stable closed loop, with this as the open loop transfer function, we need to increase the gain. Okay, and you can see all of that from the Nyquist plot. Just as a final example, let's have a look at this. E to the minus 2s on s plus 1 squared. So this is an irrational transfer function. You know, we're just keeping track of phases of a function when evaluated along a contour. It doesn't really have to be rational. Okay. When do we get things that look like that? Well, this is the transfer function for a delay. Okay. Now, if you think about the phase of a delay, the phase of delay, well, it's going to be the phase of e to the minus 2 j omega, right? Well, what's that going to be? It's going to be minus 2 omega. So as we increase omega, the phase is going to keep getting more and more and more and more and more negative. right? It doesn't stop at minus pi or minus 3 pi on 2, just keeps on going. Okay? And the effect of that on the Nyquist plot is that you get this spiralling in as we increase the frequency. That's the phase due to this part of the transfer function continuing to become more and more and more negative as we increase frequency. Okay, so when you have delay in the transfer function, you end up with many points that cross the real axis. Okay, in fact, infinitely many. Okay, and so if you, this is the Nyquist plot you get from this, right? It goes around like this, and then as you go up the negative imaginary axis, you just get the mirror image of that. Okay, so you can see that for small gain, sure, we get no encirclements of the critical point, which is what we want for closed loop stability because there are 0 open loop poles in the right half plane. But if we scale this by a positive constant, right, then once that is larger than a certain amount, we'll end up with the critical point inside here, and we'll start making encirclements of the critical point when we don't want any, right? And as you keep making k bigger, you get more and more encirclements of the critical point. Okay? So when you have delay in a closed loop, there's a limit to how big you can make the gain. Right? Because increasing the gain will always lead to encirclements. Right? Changing it from a situation where the number of encirclements may be right to a situation where it'll be wrong just by increasing the gain. So having delay in a loop always limits how much you can scale the open loop up by. Okay, and it's very easy to see from the Nyquist plot. Okay. Any questions on this? No? All right, that's just a summary of all this stuff. The key thing is that we're thinking about the closed loop in terms of the open loop transfer function. All right? And if you go right back to here, we started thinking about closed loop performance in terms of the open loop transfer function and how the shape of the open loop transfer function translates into a corresponding shape for the complementary sensitivity and output sensitivity functions, right? So wherever we want the output sensitivity function to have low gain, we just make the open loop transfer function have high gain, right? Wherever we want the complementary sensitivity function to have low gain, for example, to reduce the effect of sensor noise at high frequency, we just made to make sure that the open loop transfer function has low gain at those frequencies. So getting things right at low frequencies and high frequencies is easy. Getting things right in the middle, where the open loop transfer function crosses over, right, so to speak, in other words, where it has magnitude 1, you can end up with peaking in the sensitivity functions, right? And this really relates, as we'll see now, to how close the Nyquist plot gets to the critical point minus 1. By looking at how close the Nyquist plot gets to the critical point minus 1, you can figure out how much peaking you end up at crossover. Right? Crossover frequencies where the magnitude of the open loop transfer function is equal to 1. Right? So it's not big and it's not small, it's 1. Okay? So the Nyquist plot is going to be a useful tool in terms of understanding what happens around crossover by just looking at how close the Nyquist plot gets to the critical point minus 1. So that's what this stuff is about, if we can get there. All right. So we know if the Nyquist plot hits the critical point, right, there will be a frequency at which lambda j omega, let's say hat, is equal to minus 1, right? Well, if that's the case, 1 plus lambda j omega hat is equal to 0. In other words, this function will have a 0 on the imaginary axis. But the zeros of this function are the closed loop poles. And so if you've got a situation like this, you're going to end up with a closed loop, pair of closed loop poles on the imaginary axis. They'll always appear in a complex conjugate pair. because we're dealing with real rational functions, with the exception of possibly a delay. Okay, so we clearly don't want to be on the critical point, right? And it turns out that the closer you are to the critical point, the more oscillatory, more oscillations you get in the closed loop response to step changes in the disturbance inputs, for example. Okay, that kind of makes sense. If I'm on the critical point, I've got closed loop poles on the imaginary axis, so that's not stable. And if I kick it, right, it'll just oscillate forever in principle, right? Now, if I'm just very close to the critical point, then it's like, what have I done? I've scaled things back a little bit, and the closed loop poles vary continuously. So if I've only done it a little bit, so that I'm still close to -1, I'm going to get closed loop poles that are close to the imaginary axis, closer to the imaginary axis, so smaller real part than imaginary part. Okay, and we know that if we kicked a system like that, it'll have lots of oscillations. It'll decay very slowly, but with lots of oscillations. Okay, so you can see in this example that our Nyquist plot gets very close to the critical point. That suggests there will be closed loop poles very close to the imaginary axis. Okay, and so we'd expect to get lots of oscillations that take a long time to decay in the transient part of the closed loop response to, say, step changes in the inputs. Okay. Also, this is based on a model, right? So your real system will not be exactly like this. And if you're too close to the critical point, a little perturbation or difference, a little difference between your real system and your model may mean that for your real system, you end up hitting the critical point, right? Or moving to the other side of it, changing the number of encirclements that you make. All right? And so being too close to the critical point will give you a system that's not very robust to modelling uncertainty. Okay, so there's lots of reasons for wanting to stay away from the critical point. All right? So how do we measure how close we are to the critical point? Well, there are several ways to measure how close you are to the critical point. One is in terms of the so-called phase margin. And this corresponds to thinking about how much of a change in phase do I need to shift the Nyquist plot so that it sits on the critical point, giving me two closed loop poles on the imaginary axis. All right? So let's, for the sake of argument, just say that the open loop has no unstable poles, so no poles in the right half plane. For closed loop stability, we don't want any encirclements of the critical point. Right? So that usually corresponds to keeping the critical point to the left of the Nyquist plot. Okay? How can we make a perturbation, a change in phase of the open loop transfer function that will make it sit on the critical point? So the frequency relevant to that question is the so-called crossover frequency. It's where the open loop transfer function has magnitude 1. And if we just change the phase of the open loop transfer function without scaling its magnitude, that'll just rotate that point to sit on -1. Okay, so it relates to the phase of the open loop transfer function at the crossover frequency. Right, and the phase margin is how far away from the phase of -1 you are. There's the phase of -1, it's minus pi. So we measure the phase margin this way. Okay, as a measure of how close your Nyquist plot is to the critical point. All right. Another way is in terms of the gain margin. And this is now thinking in terms of how much can I scale lambda by, right, before I end up with a point on the critical point. Right, so the frequency here will not be the crossover frequency, it'll be some other frequency. It'll be the frequency at which lambda has a phase of minus pi, right? And if we then say, well, how much can I scale it up by before I end up on top of the critical point? That's a measure of how close you are, How much do I have to scale this up by? Well, it's 1 divided by the magnitude of lambda, where lambda has a phase of minus pi. Right, so it's a gain margin. Now, the point here is that these are just different ways of figuring out how close the Nyquist plot is to the critical point minus 1, right, which is of interest for the reasons I explained on this slide here. The other way to think about how close your Nyquist plot is to the critical point is to draw little circles around the critical point and keep on making them bigger until you just touch the Nyquist plot, right? And the radius of that largest circle is another measure of how close the Nyquist plot is to the critical point. All right? Each point on here corresponds to lambda being evaluated at a particular frequency, right? So there's your little vector lambda, right? And this little vector here from minus 1 to here will be 1 plus lambda at that frequency, right? Because if we do 1 plus this vector here, right, we get a little vector like this. I haven't drawn it to scale properly. This 1's a bit too big. So if I drew 1 little vector, 1 plus this vector, right, will give me a little vector like that. That's this guy here. All right? So drawing from minus 1 2 points on the Nyquist plot tells you about this at different frequencies, right? We know that the output sensitivity function is 1 on this. Okay? And so this sort of measure of how close we are is telling you about the peak in the sensitivity function. If this is small, right, the magnitude of this is small at a given frequency, which will make the magnitude of this big, right? So the smaller this is, the bigger the peak in the output sensitivity function. And if we go back to this plot here, the closest our Nyquist plot is to the critical point. Whoops, gone too far. Where are we? The bigger the peak we get here. Okay? So whereas if we're far away, then it's telling us the peak will not be big. Right? So this gives rise to these notions of relative stability. And the point is that you can measure it in different ways. Okay? These are the 3 main ways for doing it. Now it's important to realise that good phase margin and good gain margin does not necessarily mean small peak sensitivity, right? Because you could have a situation like this, where at the crossover frequency, we have lambda here, right? So that's magnitude 1, okay? So giving us a big phase margin, right? And then at some high frequency, we might have really small, at the frequency where the phase of lambda is minus pi, we might have really small magnitude, giving us a large gain margin. Okay, perhaps before we go into 0. Okay, but if we look at the critical point minus 1, even though we've got a large phase margin and a large gain margin because that's small, we could end up with something like this, right? Meaning there's a frequency where we are close to minus 1, right? Which will give you a big sensitivity peak. All right, so good phase margin and good gain margin is necessary for having a small peak in the sensitivity function, but it's not sufficient. Okay, the best measure of how close you are is in terms of this circle. Okay, keeping away from a circle drawn around here keeps the peak below a certain level, right? So you've just got to take care when interpreting phase and gain margins, okay? We've run out of time today, so we'll pick up from here on Thursday.
I didn't quite understand how did the circlement of the Nyquist plot is in this direction, because
Hang on, for what problem?
this is the question, lambda naught is equals to 5 divided.
Well, think about the phase. What's the if we drew the Bode plot, the phase part of the Bode plot, right? Where's this going to start? It's going to start at minus pi.
Yep.
Right?
Because these two are minus 9.
Yep. So, no. These two are at 0. This one is at minus pi at low frequency. Right? At high frequency, this will go to pi on 2. This will go to minus pi on 2. This will go to minus pi on 2. So at high frequency, we'll end up here at minus on 2. Right? So the question is, how do we get there? Well, you think about this guy. What is it going to do? It's going to go from 0 to minus pi on 2. Yeah? There's 1. Right? This guy is going to go up to minus pi on 2, but it does so slightly after, right, at 2. This guy here goes across at, well, it'll go down and reach here, but it'll be in the middle at 3. Right? Okay. So, we've got to add all these things together, right? This guy is coming down before this guy is going up, right? So the sum of these two things is always going to be like this, right? Yeah? And we end up like this, right? So we go from minus pi, right?
Minus 180.
So minus 180, we end up at minus, right, which is here. So it goes around like that. Make sense? So you've got to, don't just picture it in your head. Draw it if necessary, if you can't picture it in your head. Okay?
Thank you.
All right.
If there is a situation we got anti-clockwise, so all these examples are clockwise.
No, they're not.
Can we?
They're not always. Look, don't try to find a rule. Work it out. That's why this is why I kept on telling you to think in terms of how the phase changes as you increase frequency. It's not always in the clockwise direction.
So we can have anti-clockwise.
Well, here it's going in the anti-clockwise direction. Depends how you look at it.
This is a clockwise.
Not if you look inside here. It's anti-clockwise,
Oh, okay. Okay.
right? But to figure out which direction you're moving in, right? Just think of how the phase is changing as you're increasing frequency from a low value to a high value.
Okay.
Make sense?
Okay. Thank you.
Okay.
In this case, if the quality scale enough that this point when they close it, it's right in the critical point.
Well, if you scale this up by 1 divided by that, it'll put that on there.
I'm using K,
Yeah.
enough K to have this point.
On there. Yeah.
What will be the
Well, what is that gain? That's what I'm telling you. That gain is 1 divided by that. Yeah. If that's A and I multiply by 1 on A, what do I get in magnitude? 1. Right? Okay. So that's how much you have to scale it up by to get to here. Right? So we've scaled it up, you just put it here. So we've got a plot that looks now like this. Okay. What's the question? You'll have 2 closed loop poles on the imaginary axis because we're on the critical point. I found a frequency where lambda j omega is equal to -1. So in other words, I found a frequency where this is equal to 0. In other words, S equals j omega is a 0 of 1 plus lambda s. The zeros of this are the closed loop poles. So if I'm sitting on there, I have closed loop poles on the imaginary axis at this frequency. If I now keep going,